Hello, and welcome to this guided practice for chemistry on mole conversions. And this is the first part of a two-part series. And what I wanted to show here is just this organizer that I use for my students to be able to do the work to do the conversions. This is just a help sheet. It looks like a lot of information, but basically everything that's in the purple are the things that we're converting between. And then all of these parentheses, these are going to be our conversion factors. They come from the equivalence points or the equivalence factors that are in the typed arrows. So the typed values go together, and then the hand-drawn arrows and hand-drawn equivalence factors in those parentheses or conversion factors go together. And so this is a nice way to kind of organize yourself and use this as a tool. And I'll show you how it works on the first one, and then you can kind of follow along as needed for additional ones if that is helpful for you. So I'm going to scroll down to our first problem, and in our first three problems we are going to take a look at calculating pieces. Okay, pieces are going to be atoms, molecules, formula, units. And so in each one of these, we're going to actually use Avogadro's number. And what I like to do is I like to always underline, circle, highlight, whatever method works best for you, the amount that we start with. So it says how many atoms are in 3.5 moles of helium. So 3.5 moles is what our data point is. And we want to know atoms. So when we go to set up a problem like this, we're going to take the 3.5 moles, the data point we're given in the prompt, and we're going to use those and put those on the top. So 3.5 moles. You can put this over 1 if you like to. I just like to draw the line to show that that is in the numerator and then not in the denominator. When we do these sorts of dimensional analysis problems, we're going to actually be multiplying these conversion factors. So I start with moles and I want to know atoms. So I'm going to go back up to this handy little handout. And if you see here, to go between moles, okay, so we're starting with moles and we want to know pieces, those atoms. We're actually going to work down this list in order to go there. And so we're going to use this one on the left, this hand-drawn one on the left, in order to get there. Okay. So let's go ahead and give that a try. I'm going to come down here. I'm going to enter in this exact same conversion factor. And one of the things that helps me is using those units to set this up. So I see moles are on the top. I'm going to put moles, so per 1 mole on the bottom. And then on the top, I am going to put Avogadro's number. So 6.022 times 10 to the 23rd atoms. I can double check that my units cancel. So if a unit is on the top and a unit is on the bottom, as these are set up, they cancel. So moles cancel and I'm left with atoms, which is what I wanted to know. Okay. So the math on this, we multiply across the top, multiply across the bottom, divide top by bottom. And so in this case, it's going to be 3.5 times Avogadro's number. And when we do that, we get 2.1 times 10 to the 24th atoms of helium. And that is assuming that we are using 2 significant digits. We had 2 values in our original number. That is the number that is determining the number of significant figures that we have. All right, let's go ahead and take a look at number 2. Again, we're given a value. In this case, we're given 5 grams of sodium chloride. We want to know formula units, which is pieces. And so in this case, we're going to come back up here, and we're starting with mass this time. So we are going to go to moles, and then from moles into pieces. And so we need to know molar mass of sodium chloride. So that's the first step. So molar mass of NaCl on the periodic table, sodium is 23 grams, I round to the whole number, plus chlorine, which is 35 grams, to keep that simple, we have 58 grams per mole. All right, so let's start with our value that's given, the 5 grams. So we have 5.0 grams. We have to put grams on the bottom, so we're going to use that molar mass step first. We have 58 grams for every 1 mole of sodium chloride. Now we're in moles, but we want to be in formula units, which is pieces. That's how I describe it anyways. So for every 1 mole, there are 6.022 times 10 to the 23rd formula units. Okay, I'm going to show the intermediate math on just this particular one, but all of the additional ones will follow suit. So we multiply across the top, which means we're going to, in our calculator, multiply 5 times Avogadro's number, 6.022 times 10 to the 23rd. And then across the bottom, 58 times 1, it's going to still be 58. And then we divide top by bottom. Okay, so give that a try in your calculator. If you need calculator help, please ask during class time. Again, we have 2 significant figures. 5.0 is 2 sig figs, so we're going to round our final answer to 2 sig figs. We're going to have 5.2 times 10 to the 22nd formula units of NaCl. Okay, we're going to do the third option. We're going to start with liters of a gas at standard temperature and pressure. So for right now, you can assume that if I'm giving you liters, it is a gas and it's at STP. That may not always be the case for everything, but in these problems that we are working at the moment, that is the case. So we're going to start, and it will designate 15 liters of a gas at STP. So now if we go back up here, we're going to go out of this mass area, and we're going to be looking at volume this time. And we're going to go from volume to moles, and then from moles to pieces, just like we have in the previous steps. So let's give that a try. There are 22.4 liters per mole. That's the molar volume of a gas for an ideal gas. So we're going to start off with our 15.5 liters. We're going to do that 22.4 liters per mole of a gas at standard temperature and pressure. And then our final step, we need to get into Avogadro's number again, or use Avogadro's number. So for every 1 mole, there are 6.022 times 10 to the 23rd molecules. Getting ahead of myself here. MLQS is what I use for molecules. I know my Q's are always a little goofy. Okay. Again, you can cancel the units to help you and double check your work. Plug that into the calculator, 15.5 times Avogadro's number divided by 22.4, and I got, with 3 significant digits this time, 15.5 is 3, 4.17 times 10 to the 23rd molecules. Of CH4 or methane. All right, so that is calculating pieces. We're going to do one more series of these, and it's going to be calculating moles. Now, the great thing is, just like all roads lead to Rome, all chemistry leads to moles, and so each one of these is only one step. And so if you start with any of the extremity or those branches, they're all going to go straight into moles in the center. So I'm going to work these a little bit faster. We're going to start with 4.55 times 10 to the 21st formula units. We want to know moles. So 4.55 times 10 to the 24th formula units. And I am going to use Avogadro's number, but now I'm going to flip that conversion factor because I have formula units or the pieces on the top, so I want to have 6.022 times 10 to the 23rd formula units or pieces on the bottom, and 1 mole on the top. That's it. We do the calculation. Make sure you are very careful with how you enter things in the calculator. For this one, for proper order of operation, you should get 7.56 moles of magnesium chloride. The next one, we have how many moles are in 293 grams. Now, since we have grams, we need to know molar mass. So, molar mass, again, go back to the periodic table and find those masses of each element. So for NF3, it's going to be 14 grams for nitrogen plus 3 times 19 grams for fluorine, and that should give us 71 grams per mole. Now we go ahead and write our number, 293 grams. We put in our conversion factor, 71 grams per 1 mole. We plug in our calculator, 293 divided by 71, and we get 4.13 moles of NF3. All right, last one in this video. How many moles are in 32 liters of helium gas at standard temperature and pressure? So 32 liters. We again want to know moles. We're going to use that molar volume. So 32.0 liters. We have 22.4 liters for every 1 mole. And we should get 1.43 moles of HE gas. I hope that helps you out, and we'll do some